Project 2.2.3 Wireless Charger. This is the induction powering an analog oscillator. The first thing we must understand about magnetic induction is that a changing magnetic field is needed to induce a current. This circuit is able to create the changing magnetic field to induce current using a 5 kilo ohm resistor, two 1 nanofarad capacitors, a 220 nanofarad capacitor, 4.7 nanofarad capacitor, an IRF Z44N MOSFET, and a center tap open air coil. A MOSFET is connected to the coil, which switches on and off in response to the oscillations, which is sustaining the resonance. The 4.7 nanofarad capacitor is acting as a decoupling capacitor to filter out noise. The 1 nanofarad capacitors are acting as snubbing capacitors to control voltage spikes. The 5K is acting as a feedback resistor that is stabilizing the frequency, and the circuit is powered by a 5-volt DC source. The receiver circuit is made up of an open air coil, 10 nanofarad capacitor, 100 microfarad capacitor, 4 1N4001 power diodes, an L7805 voltage regulator, and a 10 microfarad capacitor. The diodes create a full bridge rectifier to convert the AC from the coil to DC. Then the 10 nanofarad capacitor is then used as a smoothing capacitor to filter out any ripples, providing more stable DC output. The 100 microfarad capacitor is then being used to smooth the voltage for the voltage regulator, while the 10 microfarad capacitor is smoothing out the output coming out of the voltage regulator. The voltage regulator maintains the 5 volts that are needed for charging a phone. To find the resonance frequency for the circuit, which is the most efficient frequency, we must use this formula. F equals 1 over 2 pi times square root of LC, where L is coil induction and C is the capacitance. Since the capacitor is 220 nanofarad and the induction is 68.1 nanohenries, we can do the math and we can find the frequency is 1.3 megahertz, which we've tested and we've seen is roughly correct. Another important thing that we must find is the magnetic field strength. To find this, we use the formula B equals mu 0 times I times N all over 2R. Mu 0 is a constant for the vacuum permeability in a classic vacuum. Since mu 0 equals 4 pi times 10 to the 7th Tesla's time meter over amps, and I is the current, which is 25.2 milliamps. N is the number of turns in the coil, which is 6, which is all over 2R, where R is the radius, which is roughly 2.57 centimeters. When we do this, we get it to equal 3.45 microteslas. Faraday's law of induction is what gives the value for the electromagnetic field. The formula is epsilon equals N times the absolute value of delta phi over delta t. Phi is B times A times cosine theta, where B is field strength, A is area, and theta is the angle of the coils. This circuit has a changing magnetic field, so the changing factor is going to be B, or field strength. Because this circuit has a max field strength of 3.5 microteslas, and on the other side of the wave it hits 3.45 microteslas, the total change in B is 6.9 microteslas. So epsilon equals 6 times the absolute value of 6.9 microteslas divided by 7.69 times 10 to the negative 7 seconds, which gives you a value of 5.83 volts. The final law I would like to go over is Lenz's law. This gives you the direction of the induced current. The formula is epsilon equals negative N times delta phi over delta t. This is because the induced currents will always be the opposite of the transmitting coil current. Here is the V1 design of the wireless charger stand. Here is the V2. The changes that I added to this version was splitting the stand into different bodies to prevent warping while printing. I also added an encasement for our PCB to sit on, and I also added logos to the back. Here is a PCB unsoldered, and here is a PCB soldered. Thank you for watching.